Imagine for a moment that we had a curve, and that curve started at point P, and we're only looking at a part of it, and it happens to end at point Q. And you've done enough algebra to know that you could find the slope of the line between the points P and Q. Right? And that particular line would have a slope. This is called the secant line between points P and Q. And it's specifically the secant line between points P and Q. So it's somehow related to that curve. Now, in previous work, we've considered the idea of a tangent line to a curve, so we could be considering the exact same curve, f of x, and looking at it only from points P to points Q. And it could be the case that there is a line that is tangent to this curve at P. And it might look something like that. This line is tangent at point P. Now, something important to notice, that if we were to consider the secant line from P to Q, and then look at a point closer to point P, and look at that secant line between P and that point, and then look at another secant line at another point that's even closer to P, and that line's going to look something like this, that as the point that we're drawing our secant to gets closer and closer to the point P, our secant line is getting closer and closer to looking like our tangent line. Or something else to consider is that the slope between, if we were to compare the slopes between the secant line and the tangent line, they are getting closer and closer to one another. Or, as Q gets really close to P, the secant line begins to look like the tangent line. So consider, for example, f of x equals x squared. This is a nice common example. It's always a parabola. Right, we're very familiar with this curve. We've done a lot of work with it before. We know that graphically it's going to look something like this. Its vertex is at the origin. And we would like to talk about what's happening at this curve, specifically at 1, at x equals 1. And we're going to examine it as our secant line begins at 2 and gets closer and closer to 1. So if we were considering this in terms of maybe a table of values, our table might look something like this. Our x value at first is 2, and so the output, f of x, because we're dealing with f of x equals x squared, would be 4. And our rise from the point x equals 1 to the point x equals 2 would be a grand total of 3. That would be our rise. And our run from x equals 1 to x equals 2 would be a grand total of 1, which means the slope of our secant line at that point would have to be 3. And we're going to continue to do this. I'd like you to continue to do this for x equals 1.5, then for x equals 1.1, then for x equals 1.05, and keep doing this until you get to actually the point 1. And notice what's happening to the slope. Let's go ahead and work that out. Fill out that table. Some things to notice, right? We can't actually find anything about the tangent line from x equals 1 to x equals 1 because there's no rise, and more importantly, there's no run. We can't actually get a slope. For a secant line, we can use 2 points. For a tangent line, we're only using 1 point. But based on what we're seeing, that as our second point for our secant line gets closer and closer to 1, it seems like the slope is getting closer and closer to 2. And so if I had to guess what is the slope of the tangent line to x squared at x equals 1, I would guess that it's 2. Because as I get closer and closer to x equals 1, it's becoming 2. The same idea holds if we're talking about instantaneous velocity versus actual velocity. It's very, very difficult to figure out what one's instantaneous velocity is at any specific moment in time. That's hard for us to do. A radar gun can do it, and it's using calculus to do that. That's how it's programmed. I can find my average velocity. I can find my total distance divided by my total time. But if there's no total time, I can't calculate that anymore. It's a very difficult thing. So you can fill in those charts, and I'd like you to, with regards to distance and time. And again, think through, why can't you find the instantaneous velocity at 11, given that information? Why is that so difficult? Now, if you've thought through that whole instantaneous velocity thing, you'll recognize again, the issue is one of, I don't have a change in time. I don't have a change in my x values. And so I can't calculate anything. I can't divide by 0. It causes an algebraic problem for us. So some things to notice. We can find the slope of a secant line. And you've been doing this for a long time. It's simply the slope formula, right? The function's value, the y value at a given x value, minus the function's value at some other x value, divided by the difference in the two x values. Right? All that is the slope formula. But an issue happens when we consider the tangent line because of what's happening in the denominator. Right? And so one of the things that we talk about is we have a problem with what we call h, and h is just said to be the distance or the difference between the two x values. And when we're talking about the slope of a tangent line, the issue is what's happening with h. We're still considering the function's value, outputs, at two different x values over the distance in between those x values. But that denominator is problematic, and it's problematic because the change between the two x values, we'll call h, causes some problems. That there is some distance from our given point, we'll call h, and that distance, h, between our two x values, is getting very small. Or we would say that h gets infinitely close to 0. Right, so we're considering some things that are infinitesimally small, and what's happening in those kinds of situations. That if h is 0, we can't actually come up with the tangent. And this is our starting point for differential calculus. We want to find the slope of a tangent line, and the principle is that as the 2 points that we're using to find the slope of a secant line get closer and closer to one another, they get closer and closer to what's actually happening with that tangent line. The slope of the tangent is f of x naught plus h, where x naught is just the point where you are looking. H is the distance from that point to a second point, minus f of x naught over h, where h is getting closer and closer to 0. The third equation that becomes very important right now that you get more comfortable with is point slope form of a line. If you were fortunate, this formula was hammered in your head by your Algebra 2 teacher. And if not, you need to get more comfortable using it for a variety of reasons. The point slope form is the difference between two y values equals the slope times the difference between two x values. Right, it's really just the slope formula manipulated. This is the form that you should use for linear equations in this course, mainly because you're less likely to make a mistake. Second, it's much more efficient. Let's deal with some examples. Let's consider the function f of x equals x squared plus 1. And first, what we'd like to do is find the slope of the secant between x equals 1 and x equals 3. What's the slope of the secant line? Well, okay. I know that f of 3 is 10. F of 1 is 2. So, the slope of the secant should be 10 minus 2 over 3 minus 1. Or just 4. What I'd like to come up with is what's the slope of the tangent line at x equals 2? Well, I suspect it's going to be something like this. That I need h to get really, really small. So I'm going to use h to be 0.0001. That's pretty small. Right, the distance between my 2 points is 1/10,000. So I'm going to consider what is f of 2.001, minus f of 2 all over 0.0001. And this is 5.0004. F of 2 in this case is 5 all over the distance between those 2 points, 0.0001. And when I divide that out, I get 4. So I'm going to suspect that the slope of the tangent line at the point x equals 2 is 4. Well, then the follow-up question is, what's the equation of the tangent line at 2? Well, I've got this point at 2 on the curve is 2, 5. I just plugged 2 into f of x equals x squared plus 1 to get 5. And I just did a tangent line approximation for the slope using 2.0001. Found the slope to be 4. So I would expect the equation of my tangent line to be y minus 5 equals 4 times x minus 2. And if I graph the original function, x squared plus 1, it looks something like that. And if I graph my tangent line through the point 2, 5, I'm going to see something that looks roughly like that. So these are the ideas that you're working with right now. Recognizing and seeing the relationship between secant lines, a tangent line at a given point, and coming up with the equation of the tangent line using a rough approximation. We'll be formalizing this idea of tangent line slopes shortly.